All right, let's get into this problem. So I'm just going to run through the steps. Our first step is going to be to define our loop. So just by looking at this system, we can determine that there are 3 different places for us to define our loops. We can put one right here in either direction. Any loop can go in either direction. The direction will become clear at the end. You can put one there. You can put one there. Just don't worry about it yet. And you can actually have a big loop going all the way around if you want to. And there will be situations where it might make sense to do that, but that kind of thing comes with time. For now, we're going to just stick to the standard 2 loops in the middle. So step 2, I guess we haven't written down our loops yet. I'm going to call this loop 1. And we're going to have him go in this direction. And I'm going to call this one loop 2. Okay, so now that we have that done, we go to our second step, which is to do loop rule and junction rule. If I could spell. Okay. And for this, we have loop 1's junction rule, which is going to look like, okay, so the way to think about this is you want to start at a point. I'm going to define that as my starting point, and we are going to go around the circuit in the direction of the loop. So we're going to pass up here over our battery, which is going to give us a positive voltage increase. So this guy is V1 and this guy is V2. So for loop 1, we go over the batteries, so we're going to get V1, and then we're going to go over our resistor, which is going to give us a voltage drop equal to, I'm going to define this as I1 times R1. Now this just comes from V equals IR. In this case, our current is equal to I1 and our resistance is equal to R1. So that just becomes that. And now, here's where we get into a little bit of trickiness. Since we hit this junction right here, we're going to call that a node. Our current splits off into 2 different directions, going that way and that way. And these currents aren't necessarily equal to each other. So we can't just say that the current passing through here is equal to I1. So we are going to define it as I3 because I want to put I2 on this side when I'm going through in a second here in loop 2. So we have I3 passing over resistor 3. So we're going to get minus I3 R3. And then we come back around and we hit our node. So at that point, we know that we've completed the whole circuit, and therefore this is equal to 0. Now we have loop 2. So I'm going to start right here for loop 2. We're going to come around, pass over this voltage gain. We're going to get V2. And then we're going to come around, pass over this resistor. And again, like I said a second ago, I'm going to define my current here as I2. Okay. So we're going to get minus I2 R2. And then we're going to come around again. And we're going to go to this node again. And we're going to have the same current as on the other side, right? These guys should be equal. Right here. I drew over them. Sorry, it's kind of awkward. That guy and that guy. those have to be equal to each other. The current is equal no matter where, like if you're on the same piece of wire, it's like the same. So then from here, we're going to get minus I3 R3. Then we come back around again, and we hit our node. Or we hit our point that we defined. Not node, sorry. But then we can write that's equal to 0 again. Okay. So we've extracted pretty much as much information as we can at this point. I guess I could show how to define like loop 3, but no, I'm not going to do that. That's too much work. Okay. So our next step is, as you can see at this point, we have too many undefined variables to actually solve this system. We have I2 and I3. Or I2, I3, and I1. If we only had 2 variables, like if we just had I2 and I3 in both of these systems, we would be able to like plug one into the other and use just simple algebra to solve the system of equations. But we do not have that case. We are not that fortunate. So we have to use our next rule, which is the junction rule. As we said earlier, this right here is our node. And basically what the junction rule says is at any node, the current in must equal the current out. And then I guess I can define our loop rule too, which is basically saying that the voltage over any given system is equal to 0. So now, looking at our node, we can see that we get the expression I1 plus I2 is equal to I3. And the way I think about this is we have I2 coming in towards it. I2, and we have I1 coming into it, and then once we hit our node, they go down and become I3. So that's how I come up with that expression. You could define it other ways, I guess, if you did like, I'm not even gonna go into that, but yeah, I guess I should show now that I've spoken, but I guess we could say that negative I3 goes up and turns into negative I2 and negative I1. And then if we write all that out, we get the setup I3 is equal to negative I2 minus I1. And then all of these can just become plus, and it's just the same statement. So, yeah. Fun. And then from here, we just combine our 3 equations together, and at this point I am going to start plugging in our values for our resistors and our voltages. So we're given a lot of these, or we're given all of these values. All right, so now we're gonna combine our 3 equations to give us a system that only has 2 undefined variables. Now looking at these 3 equations, it seems that the easiest move would be to either replace I1 or I2, because I3 occurs twice, so we'd have to do 2 substitutions basically to get the same end product. So we can convert this equation to I1 is equal to I3 minus I2. Always be very wary of your minus signs in these problems. They're going to get very confusing. As you can see here in a moment, we're going to have minus, and then I like to put parentheses so I don't trip myself up. I3 minus I2. That's going to be times R1 minus I3 R3 is equal to 0. Then from here we can do some multiplication. Actually, at this point, I'm going to plop in our values. So we have 2 volts, 2, and I'm just going to leave these as numbers because for the algebra, it's not really going to matter, and we know that our end result is going to be in amps. Just be careful. So R1 is going to be equal to 5. Obviously, that's ohms. We're not going to put it in. And then R3 is going to be equal to 1. So we're going to plop a 1 right there. Now this equation reduces to 2 minus, let's be careful here, plus minus plus 2 minus 5i3 plus 5i2 minus i3 is equal to 0. And then from here we can see that this becomes 2 minus 6i3 plus 5i2 is equal to 0. And we have our other equation, which is this one, which is also in terms of I2 and I3. And if we go through, so we're going to take this one a little bit further down, and we're going to write out our second loop, which is 4 volts. This is going to be 4 minus I2 R2, and R2 is 1 ohm, so that's going to just be I2, and then minus I3 R3, and we know that R3 is also 1 ohm, so that's going to be minus I3, and that's just going to be equal to 0. And then from here, we can just use algebra to solve this system for our 2 unknown variables, which are I2 and I3. We can do this through either elimination or substitution. In this case, it looks like elimination is going to be a little bit easier. I'm going to rearrange this equation a little bit. We're just going to plop I3 right here and I2 right there. This is the same thing. So we're going to have to multiply this by 5 before we do anything, which is going to give us, let's move this stuff over so we can have more room to work. This is going to give us 20 minus 5i3 minus 5i2 is equal to 0. Then we have 2 minus 6i3 plus 5i2 is equal to 0. So now we can just subtract this whole thing from the top one, and that's going to give us 0 is equal to, these cancel, and then these are both minus, so we're going to get minus 11 I3, and this is going to give us, what, 18? I feel like it should be 22 because that would be really nice, but no, looks like we're going to get 18 here. So then we can see that I3 ends up being 18 over 11, and that's in amps. So that's our answer for I3. And that's going to be the current, if we recall, right here, across resistor 3. Okay, so now we can just plug this back into our equations. I'm going to plug it into this guy right here to solve for I2. So we can just see that 4 minus I3, which we know is 18 over 11, minus I2 is equal to 0. So then from here, we can subtract everything over. Minus 4 plus 18 over 11. This is out of my mental math range. Actually, I guess I'll just do it the long way. This is going to give us minus 4 is equal to minus 18 over 11 minus I2. This is going to be plus, 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 because we can just multiply this whole equation by -1. And then subtract the 18 over 11. This is just 44 over 40. Oh, wait. Yeah, this is 44 over 11. And we could say I2 is equal to 44 minus 18 over 11. Cancel that guy out. I2 is equal to, all right, here's where it gets tricky. 3, 1, 6, 6, 2, 11. 26 over 11 amps. And now we can just plug this back into our junction rule and solve for I1. So we can say I1 is equal to I3 minus I2. So we have I3, 18 over 11, minus 26 over 11. And you might be thinking, oh no, we're getting a negative number here. This cannot be right. So we're going to get negative 8 over 11. And I want to take a second and think about what this actually is going to mean in our system. What this basically means is that we defined one of our loops in the wrong direction. Actually, did I write this right? Oh, it's I3 minus I2. No, that's right. I3 minus I2. Did I do this right? Did I do this right? Multiply by 5. Does this look good? Oh, this should be plus because we're subtracting a minus. So this is actually going to give us I3 here. And then we can see that I3 becomes 18 amps. And then from here, we plug that into here. Sorry about this. You know, mistakes are bound to happen. Like I said, don't forget the minus signs. This is why I said it. It literally happens to me all the time. So just be very, very wary. So we're going to erase all of this. And we can see that I2 is going to equal minus 14 minus I2. So I2 is going to equal minus 14. Okay, so now that we're back, I just want to actually go into depth about what the minus means here again. This minus pops up because we picked the wrong direction for our current. So since this is negative, it actually means that our current at this spot is going to be flowing in this direction. Yeah, so basically if we had chosen our loop to go around this way rather than the way we chose initially, everything going in the opposite direction, we would have ended up with a positive number here. All right. Now from here, we can literally just plug this into I1 plus I2 equals I3. Or actually, I1 is equal to I3, 18 amps, minus negative 14 amps, which is going to give us 32 amps. Check, check. All right. And that's how we solve this kind of problem.